Welcome back. In this segment, we're going to continue on with hypothesis testing, but now we're going to move up a little bit, and we'll be testing two means and two proportions. So we'll be studying what happens when, instead of comparing one average or one proportion to a value, we have two groups that we compare to each other. And we'll also be dealing with the case of averages when we have dependent or paired data. So in Chapter 10, we're studying hypothesis testing, continuing on with that, and we're testing two groups. Now, the first case that we have is when we're testing two means. And in two means, we could have independent groups, and in this case, we have two other subsets. One subset is the population variances are not known, and we've seen that before where we do the student t distribution. And the other case is where the population variances are known, and then we would do the normal distribution. These are independent groups, meaning a group of objects or individuals are in separate groups. So for example, if we wanted to test the average age of getting a driver's license in California to the average age of getting a driver's license in Oregon, we would have two separate groups, people who live in California and people who live in Oregon. If we knew the population standard deviation or variances, which is not very likely, but if we did, we would be in this case, and then we would use the normal distribution to test. If we don't know the population variance, the population standard deviation, which are most of the cases, then we use the student t distribution to test. Now, testing averages, we could also have dependent groups or paired data. With dependent groups or paired data, we're testing an average, but the groups are not independent. Somehow there's a relationship. Typically, this might be a case where there's a before or after testing. So for example, let's say we decide we want to embark on some new weight training program. And so as your teacher, I go to the gym the first day, and I try to see how much I can bench press. And turns out that I can't press anything, but I can lift 10-pound weights. So I have 10 pounds, that's my before. And then I'm going to embark on this 2-year program, and after 2 years, I go and I can press 60 pounds. Well, now what I'm interested in is my improvement. From 10 to 60, I have an improvement of 50. Somebody else might go and might be able to press 100 pounds to begin with, and at the end of the 2-year program might be able to press 150. That's a 50-pound improvement, just like I had a 50-pound improvement. Another person might start out pressing 70, and after 2 years might be able to press 200. Well, there's a 130-pound improvement. So in these cases, what we're interested in is the difference, the improvement, the difference between the after weights that you can lift and the before weights. And so we're no longer interested in who was lighter or heavier to begin with, or who could press more or less after, but just for each individual. Another type of case might be where you go into statistics and you take the final on the first day of class. And you get the final and you get your score. And then you take the final on the last day of class. Well, in between, your score hopefully first off went up, but in between what you're doing is learning material, I hope. And so what we might be interested in is how much you improved. How much did you learn from the course? That's different than saying, what was your score on the final? This is based on how much you learned in between. Another type of case might be with data that's paired, but it might not be a pre and post testing on one individual. For example, we might have couples come in, husband and wife come in for marital counseling, and you ask them on a scale of 1 to 10, how happy are you with how you divide up the chores in the house? And you might have a husband saying, 5, and you might have a wife saying 5. Well, then they're pretty evenly matched. And so we would have a difference of 0. Another case, you might have the husband saying 10. Perfect match. I think we divide up the chores perfectly. I love it. And then you have the wife coming in and saying 1. This is awful. I can't stand this. Well, there we have a difference of 9. And that tells us that there's a discrepancy. So you can do the test that way on a couple that's related together. And what we're not interested in is the individual scores, but what we are interested in is the differences. So that's another type of testing. And the last type is on proportions that we're going to be interested in. And generally, we have large sample sizes, and we're comparing two proportions. So we might have two proportions of the proportion of people who played sports in high school compared to the proportion of people who played an instrument in high school. So you might do a survey and ask one group what proportion played sport, and ask another group what proportion played an instrument, and we're interested in if these are about the same or are they different. Once we set up the problem, we do it just the same way as doing hypothesis testing before. We're going to set up the problem, and we're going to have then the null and alternate hypotheses, and then we're going to collect our data. Once we collect our data, and I'll do an example, right? I'll put up an example in just a minute. Once we collect our data, we calculate a test statistic. Based upon the p-value, we decide to reject or not reject the hypothesis. All right, here's an example that's in your text. And it says, a study is done to determine if students in the CSU system take longer to graduate than students enrolled in private universities. And you can read along in the text because this is small print here. 100 students from both the CSU and private universities are surveyed. Suppose that the following data is collected. The CSU students took on average 4.5 years with a standard deviation of 0.8, and the private university students took on average 4.1 years with a standard deviation of 0.3. Now you have a solution sheet in your textbook, and I would suggest that you do the problem out on your solution sheet. It makes it a lot easier. So when we go to do this problem, we're going to look at this, and the first thing we say is, what is it that we're testing? Well, in this case, what we're testing is the average for the CSU, something, blah, blah, compared to the average for the private. I'm going to let CSU be for CSU students and P be for private. And so it says a study is done to determine if students in the CSU system take longer. The symbol for longer is greater than. And we look at this and we say, is there an equality sign with this? And there's no equality sign, so we know that it's going to go in the alternate hypothesis. So we have the null hypothesis is that CSU students have something compared to the average for private. The alternate, though, that's the part we can decide so far. CSU is greater than the average for private. So we look for CSU, is that greater than the average for private? Now we can go back and fill in the null hypothesis. The opposite of greater than is less than or equal to. So we're going to be looking at that, less than or equal to. What we're testing is the difference in the two averages. So our random variable is the average of CSU minus the average for private. By the way, I hope you figured out that these right here are case of independent groups. Students are either enrolled in CSU or they're enrolled in private. They're not enrolled in both at the same time. So CSU minus private. So this is the difference in average time to graduate between CSU and private university students. That's what our random variable is. Now we continue along just the same way. We're going to draw the graph. We're hypothesizing that the difference is 0. And how we can see that is if you look at the null hypothesis, if we were to subtract mu sub p from both sides, the way our random variable is set up, we would have a 0 over here on the right side. So we're hypothesizing that the difference is 0. Now the actual difference, though, is 4.5 minus 4.1. So the actual difference, x bar, this is a lowercase x bar of CSU minus x bar of P. That actual difference is going to be 4.5 minus 4.1, which is equal to 0.4. So the actual difference is 0.4. Now remember, this is a number line. The labeling is our random variable, uppercase CSU minus uppercase private. And here's 0, so the actual difference is 0.4, so that has to be on the right side. And our p-value, this is a right tail test because we're going to reject in the right tail. Our p-value is this area above 0.4. And so you see that we're doing the problem the same way. All that's changing, or all that's going to change, is the arithmetic in calculating the test statistic. Now in this case, we do not know the population standard deviations, so we're going to use the student t distribution. And you can decide what technology you want to use on here. Going into the student t distribution, I'll go over and I look to see what fits most likely, and I'm doing 2 samples with a t-test. I have a student t distribution, so it's a t-test, and I have 2 samples. So we'll press number 4. And we're going to input the statistics. You could also input your data if you had collected your data into L1 and L2 and calculate from there. The first sample mean was 4.5 years. The first standard deviation is 0.8. The number in the first is 100. The second sample mean for the private universities is 4.1. The second standard deviation was 0.3. The numbers surveyed were 100. And you notice that there's an arrow going down. That means that there's more to fill in. What we're testing is a right-tailed if CSU is greater than private, so I go over and I highlight that. And for all of these problems, we are not going to pool the data, so we always press no. And now we want to calculate this. So when we calculate this, let's see what comes up here. Our test statistic is 12.88. That's a huge test statistic. Our p-value is not 3.21. Look at the whole number. This is scientific notation. This is times 10 to the negative 24th. That means we have 0.00000000. Anyways, there are 23 zeros and then 3. And since we're rounding to 4 decimal places, the p-value will be 0. Our degrees of freedom, the calculator will figure out, although there is a formula. It's not very difficult. It's just a little bit tedious. It's in your textbook. The degrees of freedom, 4.5. No, that's the sample mean is 4.5. The other sample mean is 4.1. Oh, I think I made a mistake right here. And now I just noticed that I did make a mistake. I put in 0.08 instead of 0.8. So I'm going to do this once more. We'll go over here. And I'll go down again to number 4. And now I'm going to go down and fix this. This was 0.8. Hopefully you did it correct. Let's see if I have everything else correct. Okay, now I'm going to do it again. That's a little bit better. This time we do it again and we get 4.68. That's the correct test statistic. So where that goes is we have 0 for, this is a t test statistic, and we would have 4.68. Our p-value is 0.000004, 3.6 times 10 to the negative 6th. So rounded to 4 decimal places, we have 0 for our p-value still. And so our decision would be, in this case, just like with the other cases, we're going to reject the null hypothesis, It's just like how we did it before. When we have our test statistic, we find our p-value. Our p-value is 0. That means the interpretation of the p-value is if the null is really true, then just from randomly collecting data, the probability that we would have a difference of 0.4 or greater is 0. That tells us that the probability is so unlikely that the chance is 0, so we would reject the null hypothesis, and we're going to conclude that the averages are in fact, the CSU average is in fact greater than the private university average. The next case that we're going to deal with is testing independent or dependent groups, and I'm going to go over that very briefly. In dependent groups, we have two measurements that are basically paired or the same, and we're going to do an example with that. Let's say we're doing this test here, and we do a test, and we want to know how far a baseball player can throw a baseball with the dominant hand versus the weaker hand. So we're going to have the dominant hand and the weaker hand. So if you're right-handed and you throw a ball with the right hand, that would be your dominant, and this would be your weaker, but some people might be left-handed. And let's say we have baseball players of all ages, from age 2 on up. So get somebody who could throw a ball 3 feet with the dominant and 1 feet with the weaker. Then we have somebody who can throw a ball 100 feet and 80 and 70 feet and 60 feet and 20 feet and 5 feet. And we'll just collect this because this is enough to demonstrate what we're doing here. So now we have what's called paired data. We're not interested if this average is larger than that average. That has no interest to us. What we're interested in is there a significant difference within the pairs? So we have the difference column, and we have 3 minus 1 is 2, 100 minus 80 is 20, 70 minus 60 is 10, 20 minus 5 is 15. Now at this point, also let's just do one other. Let's just say we have 20 and we have 25. It's a little bit odd that the weaker hand would be better than the dominant, but now when we subtract we have negative 5. So what we need to make sure is that we're always subtracting from 1 minus the second column and that we are consistent. It doesn't matter which way we subtract, just so long as we're consistent. At this point, we're only interested in the difference column. We're no longer interested in the dominant and the weaker data. Our only difference is the difference column. And now we're back to a Chapter 9 type problem, where our null hypothesis now is that the average, the null hypothesis is that the average difference is equal to 0. The alternate hypothesis is that the average difference is greater than 0. If it's greater than 0, we have a significant difference now. And our random variable is capital X bar sub d, which is the average difference. And now, if you notice, we have 5 pieces of data. We do not know the population standard deviation of the differences, so we use the student t distribution when we're dealing with paired data. The student t distribution, so we're hypothesizing that the difference is 0. Now I'm going to go and show you how we do this when we enter the data using the list function. We go into the list right here, and we have our data. And so I'm going to clear out from here and go and put in the data. I'll put the data into L1. So I'm going to clear out list 1. And I have now 2, 20, 10, 15, negative 5. And here are the 5 data values. And now we'll exit from here and go into the test. Now we just go into a regular student t-test. So we have a student t-test. And at this point now, I'm not entering the statistics, I'm inputting the data. That was in L1. We're testing the null to see if the null is 0. Our list is in L1. Our frequency is 1, and it's a right-tail test. And I'm going to do this twice, once with calculating and once with drawing. We're going to calculate, and we find that our test statistic is 1.8755. Our p-value is 0.0670. Our sample mean is 8.4, and the standard deviation is huge. It's 10.01. Our p-value now is 0.0670. So if we were to graph this, in fact, I'll just do this again. And now I'm going to go down all the way, and you'll see what it looks like. And I'm going to draw it instead of, and let's see why. Stat. I probably have too many things in here. Oh, my plot 1 is on. That's why we had an error. So we're going to turn off plot all the plots. Make sure you always check that. Okay, now we can graph this. I know what most of the errors are on the graphing calculator because I think I've made them all, one of them just now, by not turning off the stat plot. Okay, here is the graph, and here's the shaded region, and we have the test statistic and the p-value. So we're testing to see is the average 0. The actual average was 8.4, and that's what we would have right here is 8.4 when this is labeled x bar sub d. But the test statistic is 1.8755, and so if we were drawing this graph, we have 8.4 right here. That's the actual difference, x bar sub d. But the test statistic, t, we have 0, and we have 1.8755. And then this is our p-value right here, which is equal to 0.067. So our p-value is 0.067. So we look at that p-value and we do the same thing we do for all of the hypothesis testing. We say to ourselves, is the p-value smaller than the given alpha, or is it larger than the given alpha? Well, in this case, there was no alpha that was given. And so when no alpha is given, we're going to use 0.05. No alpha is given, and so we're comparing 0.067 to 0.05. And we say, well, the p-value is larger than alpha, and so our decision then is do not reject the null hypothesis. We're not going to reject the null hypothesis. We're going to conclude that the average difference is indeed 0. So we're not rejecting the null hypothesis. The reason is that 0.067 is greater than 0.05, and we conclude that the average difference is indeed 0. Now we've done two cases. We've done the case with independent groups when we're testing the averages. We've done the case with dependent groups when we're testing the averages. And the last case that we're going to deal with is comparing two proportions. And this is an example that is in your textbook so that you don't need to copy this down. And we'll do this rather quickly. And so we're looking at this one. And we see that a recent drug survey showed an increase in drug and alcohol use among local high school students as compared to the national percent. This was in a local newspaper rather recently. Suppose that a survey of 100 local youths and 100 national youths is conducted to see if locally the percentage of drug and alcohol use is higher than nationally. Locally, 65 seniors reported using drugs or alcohol within the past month, while nationally it was 60. And what we want to do is we want to see, is there a significant difference between the local and the national? So again, we're going to set up our hypothesis. In this case, we're setting up the hypothesis where we have the null is that the proportion of local is the same as the proportion of national. And the alternate we're interested in is the proportion of local different than the proportion of national. Our random variable, these are uppercase letters, uppercase P of local minus uppercase P of national, would be the difference in the proportions. And now we're going to do our test statistic, and we'll calculate the test statistic. So we're going to go into testing, and we're going down to 2 proportions right here. So we see that the 6th one is 2 proportions. Our first case was 65 divided by 100. The second case was 60 divided by 100. Again, we have a right-tailed test. And I think I'll just draw it in this case. I'm going to draw it. Here comes our graph. Here we would have 0. And we have 0.7203 as our test statistic. And our p-value is 0.2326. So if we were to draw the graph by hand, what we would have is a normal graph. And we would be centered at 0. And then our actual difference was 0.65 minus 0.60, which is 0.05. That's our actual difference. Here is our p-value, is this area that's shaded in right here. And we find that the p-value is equal to 0.2326. So our p-value is larger than 0.05, so we need to make a decision. Our decision would be do not reject the null hypothesis. We do not reject the null hypothesis because our p-value is larger than alpha. And so if we do not reject the null hypothesis, we conclude then that the proportions are in fact the same. So our decision is do not reject the null. The reason is that the p-value is larger than alpha. And our conclusion then would be that the proportions are actually the same. Well, that is it for Chapter 10. Let me just review what we've done in this part. In Chapter 10, we're testing 2 averages or proportions. We did the case with averages with independent groups, and there you're testing to see if one average is the same as another average where the members in the groups are unrelated. You might have a group in one area and a group in another area. And then we set up our problem. If we knew our population standard deviations, we would go into a normal test. If we don't, we go into the student t, just like we did before. Then we dealt with the case with paired data or dependent groups. And in this case, we're taking a measurement on one pair, and it might be related. So it could be a pre and a post-test pair. It could be a right hand and a left hand. It could be on a pair that goes together, such as a husband and a wife. It could be on a pair of boy-girl twins, something that's somehow related, and we're looking to see if the difference is significant or not. And the last case we did was we tested 2 proportions. Well, now you're set for this type of hypothesis testing, and we'll see what comes up in the next segment. Bye-bye.